Hello, my name is Karissa Cordero, and I'm a third-year PhD student in the Earth and Environmental Science Department. Today I'll be discussing an update in our efforts to date hydrothermal explosions in Yellowstone National Park using a technique called luminescence dating. Luminescence dating works by measuring the last time sediments were exposed to either light or heat. The idea is when their sediments are exposed to light or heat, the electrons within them become excited and no luminescent signal is able to grow. But if that energy source is removed, say the sediments become buried or they're removed from their heat source, the luminescent signal will grow and accumulate over time until the sediments are either re-exposed to light or heat or collected for sampling. This means the sediments can store information about the last time they were exposed to a significant amount of light or heat. Talking about luminescence in the context of a hydrothermal system, we must first understand what a hydrothermal explosion is. Yellowstone has an active hydrothermal system, which means that under the surface there's flowing heated water. Typically, these areas can form a caprock seal on the surface, and the pressure within the system is released through small vents across the landscape. However, sometimes these pressure release systems fail and a large amount of pressure can build up. When there's any kind of shift in the equilibrium of the area, say a small earthquake or a glacier, it is enough pressure change for that boiling water to become superheated and flash to steam. This steam escapes through the fracture of the rock and causes violent explosions of water, steam, and rock, which can be blasted out to 2 kilometers in diameter. A recent explosion in Yellowstone this summer has highlighted the need to understand these active hazards so that proper hazard assessments can be performed to mitigate risks and protect visitors and employees of the park. One of the main questions we pose is if the deglaciation of the Yellowstone Plateau was a trigger for some of these larger explosions. The idea being when the glacier melts, it can cause a drastic change in pressure, which will then cause a hydrothermal explosion. When these sediments and rocks land on the hill slopes outside of the crater, they instantly begin to cool down. In other words, they are removed from their heat source and a luminescent signal is able to grow, which could have recorded the time of the explosion. Here I have a map of our field sites in Yellowstone National Park. We'll mainly be focusing on Lower Geyser Basin, which contains a crater called Pocket Basin. Pocket Basin is a large hydrothermal explosion shown in panel A. This panel just shows you that it's still a very active hydrothermal system. Panels B and C show our sampling methodology. We take both sediments from the hill slope as well as rock cores from explosion-thrown boulders, with the idea that these ages should match, therefore giving us 2 age checks on this explosion. Here I have some of the results of the sediments that we have tested throughout Pocket Basin. You'll see by the red dots that we have sampled around the entirety of the crater, going in transects down from the top of the crater into the center of it around. This would allow us to see if there's any changes in the spatial pattern of our ages around the crater and to see if it is one big explosion or multiple. Our ages, we do 2 different kinds of testing, something called K-feldspar post-IR, as well as something called red thermoluminescence. These techniques isolate 2 different minerals, and because minerals within luminescence behave differently, it means that we have an independent age check within the study of itself. Comparing these 2 results, we see an average age of 13,000 years for this crater. This does fall within the cooling ages. These cooling ages do fall within the last glaciation of the Yellowstone Plateau called the Pinedale Glaciation, which means that they might have been a trigger from this last deglaciation of the plateau. However, we do see a couple inconsistencies in our ages, and we started to see a pattern of 2 areas of ages. First, one that was aged around 13,000 and another that's aged around 7,000. So another team went out to Yellowstone and performed something called ballistic mapping. This means that they went around the crater and they recorded the different lithologies of all of the rocks. And based on our ages as well as these patterns of ballistics, we now think that Pocket Basin was no longer one large explosion, but maybe a series of smaller explosions that could be separated using luminescence dating. We have an additional site called Mary Bay. Mary Bay is the largest hydrothermal explosion in the world and offers as our test site as there is previous radiocarbon dating already completed. Testing this explosion against our radiocarbon ages, we do see an agreement within our ages, which does lead us with confidence to continue on in the study, as well as apply it to other volcanic systems, such as the Mara eruptions in California. Thank you.